I'm Sean McLean. I'll be presenting the Team Fuchsia flow system. My other teammates are Scott Burnett and Shane Stanfield. All right, overview. I'll be going over steady state operating curve, steady state and step response, results of flow experiment, transfer function, FOPDT model, a graph of sinusoidal response, Bode plots, root locus, PI controller, and then my conclusions. All right, this is my flow system background, or the system schematic. Here's the filter wash block diagram. My input is M of T, my output is C of T, and then filter wash pump systems in the middle. My steady state operating curve goes from probably about 70 to 100, but we did it from 55 to 100, just to divide it up accordingly. Here's steady state response example for 90% input for flow versus time. The average is 18 pounds per second. There's a step up flow, 55 to 70%. Here's another graph of step up flow. Here's a K for our step up. As you can see, they're all about the same. I didn't mean to say as you can see. From this graph, they're all about the same. Our dead time, tau. Transfer function, C of S is our output function. KV to the negative T naught S, and over tau of S plus 1 is the transfer function, and 1 over S is the input function. All right, for the FOPDT model, M of T is the input function, C of T is the output function. Equations for such. Here's a graph of our FOPDT model. Motor input versus flow output for 85 to 100%. All right, here's a graph for our sinusoidal response for 0.6 hertz. And our delta C is right here. Our T is right around here. Our tau is from here to here. Here's a Bode plot and amplitude ratio for 85 to 100%. There's Bode plot and the phase angle for 85 to 100%. Here's our phase angle and F versus amplitude ratio. Here's another graph of our phase angle, amplitude ratio. Our root locus plot for 70 to 85%. Our critical damping is 0.18% for 0 degrees. Our 1/500th decay is 1.3% pound per minute. Our 1/10 decay is 3.7%. Our quarter decay is 5%. And our ultimate is 7.5%. Here's a graph for quarter decay for the P controller. It starts becoming monotonic about around 10 seconds. And then here's the critically damped Offset is 8.2 pounds per minute, percent pounds per minute. Settling time is 1.7 seconds. And our case of C is 0.5. This is for 85 to 100%. Summary table from 85 to 100% does not start becoming monotonic until critically damped around 0.5 case of C that I just showed you. It's oscillatory up until then. Here's a graph of our P control with a disturbance. Our input value goes from 60 to 75. Our output value 10 to about 20. That's it. Here's a PI controller root locus for 70 to 85%. Critically damping 0.16, 1/500 decay is 1.3, 0.1 decay is 3.7, quarter decay is 5, and ultimate is 7.5. Here's bar graphs for all of the above: 55 to 70, 70 to 85, 85 to 100. The middle region was a little off. That was my region. But Shane and Scott's region went according to a plan. It stayed about the same. Here's tau sub I times 1/3. Nine times tau sub I right here. Here's a graph for a reset windup. Here's a graph for reset wind down. T sub I in a case of C must have low settling time, be monotonic. And conclusions. Recommendations for the flow system: tau sub I would like to equal 1.9. In case of C, would like to equal 1.3% pound minute.